Here we introduce the basis of a linear subspace V in Rn as an efficient way to describe this subspace. We define vectors V1, so m vectors in V form a basis for V, so V1, V2, etc. till Vm in N. So these are all members in the linear subspace. They form a basis for V if two conditions hold. First of all, V1, V2 and Vm can be used to describe V in the sense that the span of these vectors equals V. That means V is the set of linear combinations of these vectors V1, V2 until Vm. And two, we will require that it's an efficient set in the sense that we cannot leave out any of these vectors. So these vectors are linearly independent. There's no redundant vector in this set, V1 to Vm. So for example, let's say we take one of the most trivial linear subspaces of Rn. We take Rn itself. And we pick some vector x in Rn. Then we know, we've seen already, that x allows for an easy expression in terms of the natural vectors ei, so x equals the sum of xi ei for I is equal from 1 to n. So this means that condition 1 for being a basis, so we can take these natural unit vectors e1 to en in order to create Rn as a span of these vectors. Moreover, it's easily seen that these vectors are linearly independent. Why is that? Well, each ei has a 1 on the ith coordinate, whereas the others have only zeros. So we cannot do without any of these ei's. So we may conclude that we found a basis here for Rn, which is called the natural basis for Rn. Rn has basis consisting of the standard unit vectors e1, e2 until en. And this is called the natural basis for Rn. A basis for a linear subspace of Rn is not unique. For example, if we look at V equal to R2, then we have a natural basis which consists of the standard unit vectors e1 and e2. So that's one basis. And we may also choose another one. So now consider another one. We'll show that this is actually a basis B star with e1 and the vector 1, 1. So then B star is a basis for V, for the space R2. Well, why is that? Well, first of all, we need to show that we can express any element x in R2 as a linear combination of these two vectors. So we have to show that V is actually the span of 1, 0 and 1, 1. Well, take an x in R2 so that x equals x1, x2. Then it's easily seen, we've seen this before actually, that x1, x2 is a linear combination x1 minus x2 times 1, 0 plus x2 times 1, 1. Yeah, so we may express any vector in R2 as a special linear combination of 1, 0 and 1, 1. Moreover, 1, 0 and 1, 1 are of course linearly independent. No vector is redundant. 1, 0 is not equal to the 0 vector, and 1, 1 is clearly not a multiple of the first vector, since the 1 in the second coordinate cannot be achieved by taking combinations of 1, 0 only. So here we have a new basis. So a basis is basically not unique.